Hi, I'm Jean Mercat, and I'll be presenting a paper about vehicle motion forecasting. This work is part of my PhD in the Signal and System Laboratory in Paris-Saclay, and with the company Renault. Let's consider a road scene observed from a car equipped with sensors. It detects some surrounding objects in the road scene around itself. A piece of software identifies these objects and tracks them in time. It produces tracks of XY positions for every vehicle in the road scene. Let's look at this simple situation. Here, to simplify, we'll only consider the future trajectory of the orange car. We'll consider that the future is multimodal. This means that from the past observations, several distinct futures are possible. We also consider that there are small adjustments and noise in the trajectory, adding variance to each mode. Gaussian mixtures are often used in this kind of situation, and that's what we did. We chose to represent it with 6 components. So we make many predictions, but when we look at the truth, only one true future is observed. So we want to build a model that produces all likely outcomes with their probability and variance. And what we have to produce such a model is a lot of data with only one true future for each. Our model uses the past observations to produce the forecasts, which are supervised with the observed future of the tracks. This is a self-supervised learning task. Neural networks are well adapted for this kind of task. The first problem when considering a whole road scene with many vehicles is that most neural network architecture expect a constant number of inputs, and they also expect the ordering of that input to matter. One solution from the literature is to use a constant number of inputs. The first solution for that is to use a list with a maximum size. If less vehicles are observed, zero padding is used. If more vehicles are observed, some are discarded. The list can be ordered by distance from one another. This is what is done in a complex setting in the SOPHY paper. Another ordering is to use a grid. This is called social pooling in the literature. However, neither of those are satisfying because a small change in the input could change the ordering. A different solution is to represent the scene as a rasterized image, using the pixel color to indicate present and past positions of the vehicles. This makes it a good fit to use the powers of CNNs. However, the grid map loses information with the rasterization, and is more memory expensive as it uses a sparse or redundant input. We actually want to use a dynamic number of inputs that are not sorted. Given the unsorted list of vehicle tracks, the model must produce a list of forecasts in the same order, input vehicle matching the output forecast. To do that, each track is embedded with the same function that we noted h. Then the embeddings are shared with an equivariant function that we noted g. That function may be the current vehicle embedding concatenated with, for example, the average of the other's embedding, or with a subset of those embeddings. Or it could not be the average, but the max of that subset. This is the idea behind PointNet, for example. However, this may produce a global or local context for each vehicle, but it is not specific to the vehicle. The multi-head attention that we noted transformer here produces different specific weighted averages for each vehicles, and it meets the other constraints. It is equivariant and defined for any number of inputs. So here is the whole neural network that we use. The first blocks are identical embeddings using convolutions and many-to-one LSTMs. Then the embeddings are concatenated for the multi-head attention to be performed. Each vehicle embedding is then unrolled in time using one-to-many LSTM. Another multi-head attention is performed in time. Finally, the output is decoded with a linear layer. The specific activation function produces the Gaussian mixture output. This model is trained with the negative log likelihood function. Let's take a closer look at the multi-head attention block. We chose to use 8 attention heads. Each one of them performs the same computation with a different set of weights. This is the key query value attention mechanism described in the Attention is All You Need paper. Once trained, each head specializes to a specific attention pattern. Some of them are interpretable. Each head performs a specific weighted average of the values for each extracted track. The weights can be interpreted as the attention that a vehicle throws onto the others. They can be represented in a matrix. Each row corresponds to each track and defines the weights over all other tracks. Another way to represent the attention is with a graph. The ij weight from the matrix scales an arrow going from the vehicle I to the vehicle j, or a circle if I equals to j. The arrow colors match their orientations along the colored circle. This head attention is quite difficult to interpret. Here, it's a lot clearer. This head mainly pays attention to the leading vehicle in each lane. Not every head is easily interpretable, even if it doesn't look random. This one is clearly sensitive to the distance. This last pattern goes from one vehicle to the one in front of it in the same lane. The vehicle 0 is interesting because it's in between lanes and points toward 2 vehicles. We use the negative log likelihood to define the loss. However, other indicators are used to define performance. A modified version of this model was ex aequo for the first prize in the first Argoverse Motion Forecasting Challenge held in NeurIPS 2019. It was judged using the minimum final displacement error of a 3-second forecast for one vehicle in the scene. The minimum means that only the best among the 6 proposed forecasts is considered. Other metrics are used. The minimum average displacement error considers the whole time sequence for that trajectory. If the true final observed position is at more than 2 meters from any of the proposed forecasts, the forecast is considered to be a miss. The miss rate is very interesting as it gives a sense of diversity to the forecast propositions. For the new challenge, it's no longer the final displacement error that counts, it's the miss rate. And new propositions have been made. The 2 winning teams from the last session are now 4th and 8th. It's a very active field. The main criticism for our work, that is also very justified, is the lack of an ablation study. Indeed, the second multi-head attention block could be ablated. However, when we tried that ablation during the training on the NGSIM dataset, it diverged, and I'm still not able to know why. However, it was successful on the Argoverse dataset. We used the modified version of this model to include vehicle-to-lane attention, and the result of the ablation showed similar but degraded results. Let's conclude. We've combined long-range interactions with a joint on multimodal forecast. The forecast modes are diversified without the need for maneuver classification. We could interpret the vehicle-to-vehicle interaction patterns that are learned. This model can be extended with other types of road scene perceptions, such as lanes. Thank you for your attention and have a safe conference from home.